this recording, we'll be looking at a couple of brief topics. We'll be looking at the center of mass of a system of objects. It also will be introducing the motion of the center of mass and momentum. So up until this point, we've been treating objects as point particles. We haven't been looking at the more complex motion. So if you have an object that's a little bit more complex, if it is an extended object and we throw it through the air, for example, this baseball bat that's tossed through the air, the center of mass of the object is the point of the object that moves in the way that we have been describing up until this point. The center of mass of an object is the point that moves as if all of the mass were concentrated there and all of the external forces are applied there. And so to look at a couple of situations, in this animation, we have a baton that's going to be thrown through the air. And so the baton has these two white balls and it's connected by a stick. The red ball that's there is marking the center of mass of the object. And so when this is thrown in the air, you can see that the motion of each end of the stick is somewhat complicated, but the center of mass of that baton will follow the parabolic path that we had said that you should have from Newton's laws. Again, we said that the only force acting is the force of gravity. An object will move in a parabolic path. This is referring to the center of mass of the object. One more example that's very similar to this. We have this bowling pin, and it's a juggling pin. And if it's thrown through the air, it's going to follow some complex path. And I can have this record where it's at different points in its motion. And so again, we have this complex motion. If I looked at the two endpoints and I had those tracked as this was moving through the air, again, each end is moving in a complex path. It's not moving in a straight line. But looking at this, the center of mass of this juggling pin is not going to be at the center of the object, which is I labeled in the diagram. It is at point B. And so if I turn this on and I look at that path, I see that that red line is tracing out a parabola. The center of mass of that bowling pin is the part of the bowling pin that does move as if it was all the mass was concentrated there. That is the point that moves in the parabolic path. And so if we learn how to deal with problems involving the center of mass, if you want to calculate the center of mass, the position of the center of mass, again, in this notation, XCOM, the COM stands for center of mass. If you have two objects, the way that you calculate the position of the center of mass is a weighted average of each of the masses with their positions. So if you have two masses, it would be the mass of the first object, m1, times its position, x1, plus the mass of the second object, m2, times its position, x2, and then you divide by the total mass. If you had more than one object, then you would just continue this. You would have m3x3 plus m4x4, and you would include all of the different objects that you have. And then you would divide by the total mass. That would be m1 plus m2 plus m3 plus m4 plus however many masses you have. You divide by the total mass. And this could be rewritten as a sum where you can write it as 1 over the total mass times the sum of each individual mass times the position of each individual mass. And this can be done for the x and the y and the z directions. So this equation right here, writing the center of mass as a vector, is actually 3 equations in one. It's saying that the x-coordinate of the center of mass is m1 x1 plus m2 x2 plus m3 x3 divided by the total mass. The y-coordinate of the center of mass, you would, instead of looking at the x positions of each of the objects, you would do m1 times its y position plus m2 times its y position plus m3 times its y position. And you would divide by the total mass. The z-coordinate of the center of mass is exactly the same thing. m1 z1 plus m2 z2 plus m3 z3 over the total mass. Now, an important thing to note is the center of mass is not always within the object. If you have a donut, the center of mass of the donut would be at the center where there isn't anything. Or if you have a horseshoe, the center of mass of the horseshoe, there's nothing physically located there. But those would be the coordinates of the center of mass. Again, the center of mass is not always at the center of the object. It depends on where you have all your masses located. It's a weighted average of the locations of all of the masses. And so if we look at an example problem, we have these 3 particles. M1 is located at the origin and has a mass of 1.2 kilograms. M2 is 2.5 kilograms, and it's located at 1.4 meters along the x-axis. So again, in the drawing, those are marked off in centimeters, but it is at a position of 1.4 meters. And M3 is 3.4 kilograms. Again, these are on the corner of an an equilateral triangle with edges of length 1.4 meters. And so just to get the x and y coordinates of M3, the x coordinate is going to be 0.7 meters. And the y coordinate you could get from a little trigonometry. This is 60 degrees. This is 1.4 meters. And so this height would be 1.4 times the sine of 60 degrees, which is 1.21 meters. And so the x coordinate of the center of mass would be 1.2 kilograms times its x coordinate, which is 0, plus mass 2, which is 2.5 kilograms, times its x coordinate, which is 1.4 meters, plus m3, which is 3.4 kilograms, times its x coordinate, which is 0.7, and then it's that whole thing divided by the total mass, which is 1.2 plus 2.5 plus 3.4, which is 7.1 kilograms. If you multiply all these out, you get that the x coordinate of the center of mass is 0.83 meters. If I wanted to find the y-coordinate of the center of mass, I would do the exact same thing except for the y values, the y positions. So mass 1 is 1.2 kilograms times its y value, which is 0. Mass 2 is 2.5 kilograms, but it's also located at a y value of 0. And mass 3 is 3.4 kilograms, and it's at a height of 1.21 meters. Again, I'm going to divide by the total mass of 7.1 kilograms. And if you multiply this out, you get a height of 0.58 meters. So again, this coordinate of the center of mass is at x equals 0.83 and y equals 0.58. And so it's not located at the center of that triangle. There was, mass 2 was more massive than mass 1, so it pulls the center of mass to the right. And if we look at M3, M3 is slightly less than M1 and M2 added together. So that pulls the center of mass slightly below halfway. M3 was at a height of 1.21. This height is a little bit under half that at 0.58. Again, kind of looking at some of those things. This is another example where we have three masses. Again, you could go through and see where the center of mass is. The x-coordinate of the center of mass. I say that ball 1 has a mass of 1.2 kilograms. It's at an x-coordinate of 0.4 meters. So this would be 1.2 times 0.4 plus 2.1 times negative 0.4 plus 1.7 times 0.1, and it would be that whole thing divided by 1.2 plus 2.1 plus 1.7. And so working this out, you get for the numerator negative 0.19, and the total mass is 5 kilograms. So negative 0.19 divided by 5 is negative 0.038 meters, which is what they have here. The x-coordinate of the center of mass is negative 0.038 meters. You could do the same thing for y. You have 1.2 times 0.7 plus 2.1 times 0.7 plus 1.7 times 0.2 divided by 5 kilograms. So you get 2.65 over 5, which is 0.53, which again agrees with the calculation there. And looking at this, again, if I adjust the mass of the different spheres, if mass 1 is 0, then the center of mass lies along this line connecting masses 2 and 3. If mass 2 is also 0, then the center of mass is right in the center of mass 3. It's at its location. If, again, mass 1 is 0, if I make mass 1 and mass 2 equal to each other, then the center of mass is right at the center of the two. If mass 2 is bigger, the center of mass is closer to mass 2. If mass 2 is smaller, the center of mass is closer to mass 3. So you can see that it's averaging together the locations of the objects and their masses. If it has more mass, it's counting that location more. And if I look at masses 1 and 2, I can move this around. If mass 1 is bigger, the center of mass is closer to mass 1. If I make mass 2 get closer to mass 1, then it pulls the center of mass closer. And again, when they're equal to each other, it's halfway in between. Again, if mass 2 would be bigger, the center of mass goes closer to mass 2. So again, the center of mass can be calculated for any number of objects. If you have a solid object, then you're doing a similar thing, except you're breaking the solid object up into pieces. And so the formula is still 1 over the total mass, and then you're summing up all of the individual pieces. So if I had a bar, I could break that bar up into little pieces dm, and I look at the x coordinate of those pieces, and I add up all of those pieces. And so it's an infinite number of pieces, and so this is an integral in calculus. And we can go through, and if we have the x coordinate of the center of mass is 1 over the total mass, we have this relationship that the mass of each little element is the density times the size of that piece. It would be the volume if we're looking at 3 dimensions. And so we have that this is the integral of x. Again, dm is the density rho times the volume v. But this total mass, looking at this, the total mass is the density times the total volume. And so we get that the x coordinate of the center of mass is 1 over the density times the volume of x times the density rho times dv. So we can see that those densities divide out, and we get this equation that the x coordinate of the center of mass is 1 over the total volume times the integral of x with respect to the volume. Again, you have the same thing for y, and you have the same thing for v. In general, these calculations can be somewhat complicated. There will be an example of looking at this for 1 or 2 different objects in a separate video. Again, if you have a constant density, you can pull the density out of the integral. If the density is not constant, then you must use this equation right here. You can't look at the volume equation. You would need to use this equation that has the total mass in it and you would need to use this equation where the density is a function of the volume, and you could go through and you would have to integrate that. Again, the volume you would need to write in terms of x by using disks or shells. So it's exactly the same as using disks and shells to find volume in calculus, except you have this extra x that's in the integral. Again, there will be a separate video looking at an example of a circular cone and trying to add it up and find the center of mass of the cone. If you have uniform objects, then the simple thing is that the center of mass of the uniform object is going to be right at the center of the object. So if this center of mass is made up of 3 uniform metal bars, each one with a length of 10 meters and a mass of 2 kilograms, that means that the center of mass of each of these bars can be looked at as being at the center of this. So you can treat it as a 2 kilogram object. This would be at a height of 5 meters. This would be a 2 kilogram object. Again, you have an x coordinate of 5 and a y coordinate of 10. And this would be a 2 kilogram object. Again, the x coordinate would be 10, the y coordinate would be 5. So if I wanted to find the center of mass of this object, first by recognizing that I could treat this bar on the left as just a single point mass located at its center. I can treat this bar on top as a single point mass located at its center. I can treat this bar on the right as a single point mass located at its center. I've turned this from something that looked complicated into finding the center of mass of just 3 point masses. And so the x coordinate of the center of mass would be 2 kilograms times 0 for that first mass, plus 2 kilograms times 5, plus 2 kilograms times 10, divided by the total mass of 6. So that gives me an x coordinate of the center of mass of 5 meters, which shouldn't be surprising. It's going to be halfway in between because of the symmetry of this, because the left side and the right side look exactly the same about that line of symmetry, then the center of mass is going to be right at the center. The y coordinate of the center of mass, though, is going to be a little bit different. It's going to be, for the first mass, it's 2 kilograms times 5 meters, plus 2 kilograms times 10 meters for the second object, plus 2 kilograms times 5 meters for the third object, divided by 6. And so doing this, we get that the y coordinate of the center of mass is 40 over 6, or 6.67 meters. Again, because there's not a bar down at the bottom, if there was, that was uniform, then the center of mass would be right at the center at a height of 5 meters also. But because there's not, again, it's not symmetric about this middle here, because there's more mass up here than there is down here, which there's none. And so that pulls the center of mass up above the center, and it's putting the center of mass somewhere about right there. Again, there's not physically anything located there at that point. If something is stable, then that means that the center of mass must be directly located over the base. And so with this gymnast, even though she might not actually know how to calculate her center of mass, by adjusting the shape of her body, she's able to balance herself, and she is balanced if her center of mass is directly above her hands, which is the support point. And so her center of mass is probably approximately somewhere around right here. And so an important property of the center of mass is that something will be balanced if the center of mass is directly over the base, and something will tip over if the center of mass is not located directly over the base. If her center of mass would be over here, we'll see later on that that would cause her to rotate around counterclockwise. That would cause her to fall down. If her center of mass is over here, it would cause her to rotate clockwise, and again, she would tip over. But if her center of mass is directly over that support point, like it is in this picture, then she's perfectly balanced. So we had looked at Newton's second law for a single object. Newton's second law said that the net force equal the mass times the acceleration. If you have a system of particles, if you have more than one particle acting, if you look at the net force acting on that system, and more specifically, if that net force is referring to the sum of all of the external forces on the system, so that's forces that are from something that's outside of the system on something that's inside of the system. If we look at the sum of all of the external forces, those cause an acceleration of the center of mass of the system. So the net external force on the system equals the total mass of the system times the acceleration of the center of mass of the system. Again, the total mass of the system, we're assuming that no mass enters the system or leaves the system as it moves. So this is referred to as a closed system. There's no exchange of mass with its surroundings. And again, ACOM, that's the acceleration of the center of mass of the system. Again, it's not talking about the acceleration of any one of the individual objects. It's just referring to the acceleration of the center of mass of the system. In the very beginning animation, when we showed the baton that was being tossed in the air, we were looking at the center of mass of the system, and that was the one that behaved just like projectiles that we talked about in chapter 4. The end points of the baton, those moved in a much more complicated fashion. Their accelerations would be much more complicated, but the acceleration of the center of mass was the 9.8 meters per second squared downward like we had described before. One of the things that this means is if you have something that's moving and it explodes, the center of mass of the fragments, if all you had was an internal force causing this to explode, the center of mass of the fragments would follow the same parabolic trajectory that the original rocket would have followed if it had not exploded. And so to look at a slightly simpler model of this, we have this ball that's going to be shot into the air, and it's going to explode into two equal pieces at the top of its parabolic path. And so if we run this, we can see that it explodes, and one piece shoots farther to the right, and one piece shoots to the left. And at first, it might be a little bit difficult to see where the center of mass is. And now the center of mass is located at the red dot, and you can see that the center of mass stays half, because these are equal size pieces, it stays halfway in between the two objects. And that center of mass does follow this parabolic path. The center of mass moves exactly as it would if those pieces had never exploded. Again, assuming that this was only an internal force that caused them to explode apart. If it is, then there was still only the force of gravity as the net external force on the system. And so its motion behaves exactly as if it would have if it was a single object moving under the influence of gravity. Here we have three particles, and each one has a force acting on it, and we have the center of mass given in the problem. But we can go through and we can find the net force on this system, and we can use it to find the acceleration of the center of mass of the system. And so we have force 1, which is 6 newtons. We have force 2, which is 12 newtons at a 45-degree angle, which if you break it into components, you get 8.485 newtons for both the x and the y. And then force 3 is 14 newtons. So if you found the net force in the x direction, it would be 8.485 plus 14 plus -6. And so that adds up to be 16.485 newtons. The net force in the y direction, there's F1 has no y component, F3 has no y component, so it's just 8.485 newtons. If I wanted the acceleration, just the x component of the acceleration, it would be 16.485 newtons divided by, and this is where I have to be careful, I have to make sure that I use the total mass. So the total mass is 4 kilograms plus 8 kilograms plus 4 kilograms. So you have 16 kilograms total. So this is 16.485 divided by 16, which is 1.03 meters per second squared. The acceleration in the y direction is 8.485 divided by 16, which is 0.53 meters per second squared. So the overall acceleration, you would add those two components together, 1.03, 0.53. You would use the Pythagorean theorem, and you would get 1.184 meters per second squared. And that angle would be the inverse tangent of the y component over the x component. So it'd be the inverse tangent of 0.53 over 1.03, which is 27.23 degrees. And if we would look at this, the net force on the system is at an angle of 27.23 degrees. And so that will be the direction of the acceleration of the center of mass of the system. The center of mass is going to be accelerating up to the right. Again, each of these particles is going to be moving in different directions, but if we look just at the center of mass, that center of mass is going to be accelerating up to the right. In this video, I have two carts that are going to be colliding and sticking together. And this cart on the left is a little over 1 kilogram, and this cart on the right is a little over a half of a kilogram. And we can see that the position of this left cart we have this marked right at the center. Because this is approximately a uniform object, the center of mass of this cart by itself would be at about its center. So we can treat this as a single point mass, and we can treat this as a single point mass. And if we looked at their positions, if I would calculate the center of mass, that would be the position of this orange dot. In fact, showing that's where this spreadsheet is. It has the x coordinate of the cart on the left and the cart on the right. And by looking at the center of mass equation, we can calculate that position of the center of mass. And so as I look at this, if I look at the center of mass, this cart on the right is not moving. This cart on the left did move. And so if you calculate the new position of the center of mass, that's this dot right here. And so as I step through, we'll be able to see how the center of mass moves. And so because those dots are equally spaced, then the center of mass is moving at a constant velocity. And then these two parts stick together. And so now we can see that the blue dots start to move. This cart on the right is starting to move. But again, as I step through, I can see the center of mass. The thing that's important with this is as these two carts are sitting there, the cart on the left was sliding towards the cart on the right. If I treat the two carts together as my system, then when they collide, the only force acting on the system is an internal force. And so if the net external force is 0, then the acceleration of the center of mass should be 0. And so if we look at the center of mass, the distance that it travels in each frame of the video stayed the same. The velocity of the center of mass stayed constant before and after they collided. If I looked at the graph of the position as a function of time, we can see that for this red cart, it had a certain velocity before it collided. And so the slope of this line would be the velocity that it has before it collided. And then it has a different velocity after it collided. We can see that the slope got smaller. It went from 0.387 meters per second down to 0.2499 meters per second. The cart on the right, we can see that it wasn't moving at the beginning, and then it did start moving. So we have that velocity increasing. But if I look at the slope of the yellow dots, I get a straight line. The position of the center of mass of the system changed at a constant rate the entire time. It moved at a constant velocity of 0.2552 meters per second the entire time. That means if the velocity didn't change, the acceleration of the center of mass was 0. This shows that even though the motion was slightly complicated, we had one object slowing down, one object speeding up. Because the external forces were 0, the center of mass just moved along at a constant velocity the entire time. Okay. In this problem, we have two people in a canoe, and they're going to be exchanging places. And so first, to kind of see what's going to happen, there's an animation that's similar to this that I want to look at. So here, you have to use your imagination a little bit, but we have a man standing on one end of a canoe, and then this red object is the canoe. And so right here, this is the we can treat the man as just all of his mass concentrated at this point. We're looking at just his x coordinate. So this is kind of the man, the center of mass of the man. This dot right here is the center of mass of just the boat. And this square is the center of mass of the system. And as we look at this, as the man walks towards one end of the boat, the friction on his feet causes the boat to slide in the opposite direction. And so we can see that the man is moving to the right and the boat is moving to the left. But because the net external force is 0, the center of mass is staying at exactly the same location. And so that we have the center of mass being at the same spot. So the boat moved one way, the man moved the other way, but the center of mass was not changing. So that's what we're going to have in this problem that we're looking at. So we have Ricardo with a mass of 80 kilograms and Carmelita with a lighter mass, but we don't know it, and they're in a canoe that's 30 kilograms. And so when the canoe is at rest, they exchange seats. Their seats are 3 meters apart and located symmetrically with respect to the canoe's center, which is going to be the center of mass of just the canoe. And Ricardo notices that the canoe moved 0.4 meters relative to a log in the water. So the canoe moved 0.4 meters relative to the fixed water. And he is able to use this to calculate the mass of Carmelita. And so if we look at drawing of the situation, we have Ricardo with a mass of 80 kilograms. We have the canoe with a mass of 30 kilograms. And I'm going to look at where Ricardo is as x equals 0. That means that the center of mass of the canoe is located at x equals 1.5. And then we have Carmelita. She's wearing a dress. And she has an unknown mass, but she's located at 3 meters. And so the center of mass before they moved is 80 times 0 for Ricardo, plus 30 times 1.5 for the canoe, plus m times 3 for Carmelita, divided by the total mass of 80 plus 30 plus m. And because they tell us that Ricardo is more massive than Carmelita, that means that the center of mass is going to be somewhere in between Ricardo and the center of the canoe. It's going to shift the center of mass to be slightly to the left of the center of the system. The key to this problem is recognizing that as they switch spots, the center of mass of this canoe is going to stay in exactly the same location. It's not going to move. The canoe itself moves. We're told that the canoe shifts 0.4 meters. So it went from 1.5, the center of the canoe went from 1.5 meters. Now it's at a position of 1.1 meters. We have Carmelita, and she's at a position of negative 0.4 meters. And we have Ricardo. So if this was 3, this is 2.6. And so the center of mass after they trade places would be m times negative 0.4 plus 30 times 1.1 plus 80 times 2.6 divided by 80 plus 30 plus m. The key to this problem was recognizing that these two must be equal. And so I can set those two equal to each other. And so before they traded places, if you work out that numerator, you get 45 plus 3m, and then the denominator is 110 plus m. I'm going to set that equal to, in the second equation, we have negative 0.4 times m plus 241 divided by 110 plus m. If these are equal to each other, I can multiply both sides by 110 plus m. It just means that these two numerators are equal. And so we have 45 plus 3m equals negative 0.4m plus 241, or 3.4m equals 196, or the mass of Carmelita is 57.647 kilograms. Again, by understanding that the center of mass of the system needed to stay in exactly the same spot, so even though everything else shifted around, the center of mass of the system stayed in exactly the same location because there were no external forces acting on the system. We were able to figure out the unknown mass from how far everything else shifted. The last thing in this chapter is the introduction of the concept of momentum. And momentum will play a much bigger role in the next chapter as we look at collisions. But just introducing the idea of momentum. The momentum of a particle is defined as the mass of the particle times the velocity of the particle. Momentum is going to be a vector, and the direction of the momentum vector will be exactly the same as the direction of the velocity vector. The unit of momentum is kilogram meters per second. There's not anything extra. There's not another name for that. It's just kilogram meters per second. And momentum, again, since momentum is mass times velocity, net force actually is, more accurately defined in terms of the rate of change of momentum as opposed to just mass times acceleration. The net force on an object is the rate of change of the momentum of the object. If you have a constant mass, the derivative of the momentum with respect to time means the derivative of mv with respect to time. But again, if the mass is constant, then that's just the mass times the derivative of the velocity with respect to time, which is the mass times the acceleration. The reason that this is the more accurate way of writing the net force is because there are some situations where the mass changes. For example, rocket propulsion. That'll actually be something that gets looked at the end of the following chapter. But if we look at this equation, we can take the derivative of mv, and we would use the product rule. So we would have v times the rate of change of mass, dm dt, plus m times the rate of change of the velocity, dv dt. So we would have two pieces, and we would have to put both of those pieces together to look at the net force on an object. And if we have a system of objects, then the total momentum of the system is the momentum of each one of the individual objects together. So the momentum of the system would be the momentum of object 1 plus the momentum of object 2 plus the momentum of object 3. Again, remember these are vectors, so we're adding these momentum vectors together. But momentum 1 is mass 1 times its velocity. Momentum 2 is mass 2 times its velocity, and so on and so on. So you're adding all of those momentum vectors together. And it works out that this could be written as the total mass of the system times the velocity of the center of mass of the system. If we think back to the video that I showed with the two carts colliding, the velocity of the center of mass of the system stayed constant. That showed that the linear momentum of that system stayed constant. The individual momenta changed. The momentum of the first cart changed, the momentum of the second cart changed, but the total momentum of the system did not change. That's going to be the whole key to the next chapter when we talk about conservation of momentum. So the linear momentum is equal to the product of the total mass of the system and the velocity of the center of mass of the system. Again, for a constant mass, the rate of change of the total momentum of the system will equal the mass of the system times the acceleration of the center of mass of the system, or the net external force on the system will equal the rate of change of the momentum of the system. This is going to bring us to the idea of conservation of momentum in the next chapter. So the final thing I'd like to look at is just looking at the change in momentum of a system. And so here we just have a single object. We have, this is going to be highlighting the fact that we have that momentum is a vector. And so we have a 2-kilogram toy car that's taking a turn on a track. It's going from moving straight down to moving to the right. And its speed is 0.5 meters per second before the turn, and it's 0.4 meters per second after the turn. And so initially, in the x direction, there's 0 momentum. And the momentum in the y direction is going to be 2 kilograms times negative 0.5 meters per second. Again, it's negative because it's moving downward. I'm going to make up positive and to the right positive. So this is negative 1 kilogram meter per second. After the turn, the momentum, the final momentum in the x direction is 2 kilograms times positive 0.4 meters per second, which is positive 0.8 kilogram meters per second. And the final y momentum is 0. So the initial momentum is straight down. The final momentum is to the right. And so change in momentum is the final momentum minus the initial momentum. And so looking at this, I can find the change in the y direction, which is 0 minus negative 1. So the change in momentum in the y direction is positive 1 kilogram meters per second. The change in momentum in the x direction is the final x momentum of 0.8 minus the initial x momentum of 0. So that's positive 0.8 kilogram meters per second. And so the total change in momentum is going to be 0.8 squared plus 1 squared which is 1.28 kilogram meters per second. And that angle would be the inverse tangent of 1 over 0.8, which is 51.3 degrees. Which also, if we remember what it means to subtract vectors, this means the final momentum plus the opposite of the initial momentum vector. And so if the initial momentum vector is down, the opposite of that initial momentum vector is upwards, and it's 1 kilogram meters per second. The final momentum was to the right, and so the overall resultant vector is this vector right here, which is the same one that we found. The total change in momentum of this car is up to the right at a 51.3 degree angle. We're going to see that that means that the force that acted on it was in that exact same direction. The force is what causes that change in momentum. Again, in the next chapter, we're going to be going through conservation of momentum and looking at a lot of problems with that. But this is a quick chapter that's just really introducing the idea of center of mass and really looking at systems where the external force is 0 and seeing that the center of mass doesn't move or it continues moving at a constant velocity, and kind of learning about the idea of momentum.